Okay, guys, so in this video, what I'm going to do now, I'm going to conclude chapter number 10. I'm going to cover 10.10 and 10.11. And these topics will be a limiting reactant problem topics, limiting reactant concept. And 10.11 will be the what's called percent yield problem. All right, so what I'll do is I'm going to actually use my reaction that I presented in the previous video when I had N2 gas plus 3H2 gas yields 2 NH3, okay, 2 ammonia molecules of or moles of gas. Okay, now what makes a problem limiting reactant problem? Here is what it makes it now. If I'm given here, let's say 15.2 grams of nitrogen, and I'm not being mentioned about the amount, let's say, of this hydrogen, that means this is not a limiting reactant problem, and that means it implies that you have excess grams of hydrogen here, or moles. Now, if they actually in the problem state, well, now you got 10.2 grams of hydrogen, that what makes it now a limiting reactant problem, because you're given the amount of both reactants. Again, in the previous case, it was not a limiting reactant problem because you only were given amount of one reactant, and the second one was not mentioned, or was mentioned that it's excess amount. That is not a limiting reactant problem. It's like, remember when we built the table, we had 4 legs plus 1 top, and then we got 1 table. 1 table, guys. So remember, guys, we had here, let's say 20 legs, and I don't mention, and they have, let's say, excess amount of tops. That is not a limiting reactant problem because you have so many now tops that you can pretty much utilize all of the legs to build the tables. And of course, you can build now 5 tables here. Now, but what if you're given now 2 tops in here? 2 tops in here. 2 tops in here. And let's say to produce, now the question is, how many tables are you going to produce? How many tables can you make? All right, let me just erase that. How many tables can you build? Can you build? Well, this is the question mark here now. So it is important now to understand that, remember, guys, we have our conversion factors. 4 legs, important here, I'm circling it. 1 top, important, I'm going to circle, produces 1 table. So now, how is this now? We can make it now a limiting reactant problem. And the way we make it, as here, we given the amount of both things that we're going to put together to produce something that is the product here, which in this case, stable. Again, I'm trying to link now the macro world to the micro world of the molecules. All right, so how do you do it? Now, these 4, 1, and 1 are very important numbers because they are like stoichiometric coefficients here will be used to convert from the, the legs in here on tops to the tables. All right. So remember in the previous video, when I didn't have a limiting reactant problem, I was only worried about converting just the legs into the tables. But here, though, I have to convert both the legs and the tops into number of tables so that I can compare the two and choose the one that will produce the least number of tables. And that will be my limiting what's so-called reactants, in this particular case, making the tables. All right, let's do it. So I got 20 legs times 4 legs. Again, important. This came from this coefficient here with 4 legs, producing 1 table. Cancel, canceled. 5 tables. Now, what about tops now? I got 2 tops. And remember, the top 2 table ratio is 1 top, always needed to produce 1 table. Cancel, cancel. And so all you can do now here, you can only build, guys, in the reality 2 tables because you don't have enough tops to build 5 tables. And so now the tops will be nothing else as the limiting reactant. And the legs will be what's called an excess reactant. Okay, so here we, more concerned again about the limiting reactant. That's why I pointed now the limiting reactant here to the tops, where the legs now here is the excess reactant. Now, how do I bridge now from here and I go to my now reaction here? Very simple, guys. All you have to do is 15.2 grams of N2. We need to convert now, and also the 10.2 grams of H2, convert into the moles of the same product. And the next step, which you have to do, just compare these two numbers that you're gonna get here and choose the one that is the smallest number. And that will be your, whichever gives you guys the reactant, the smallest number, most of the product will be called a limiting reactant here. All right, let's do it step by step. So I got 1 mole of N2, which will be 28.02 grams of N2 times canceled. And all you have to do now to say 1 mole of N2 now produces here, guys, 2 moles of NH3. Okay, so let's get now the moles here for, based on the first reactant here. So it's 15.2 divided by 28.02 and then multiply by 2. Okay, so you got here 1.08 and little 5 in here. So this is now the first answer here, similar to this, for example. Now, the next one, I will do the same thing now for hydrogen now elements. So it's going to be 1 mole of H2 contains 2.016 grams of H2. I don't know why I'm putting here the N2. Okay, H2, canceled. And my next step, I need to convert now my moles of hydrogen. There it is, there it comes. 3 moles of H2 now to 2 moles now of the product. 2 moles of NH3, almost there, guys. So 2 here, 2 moles, right? So now let me get now number of moles of the product based on the grams of the hydrogen element here. 10.2 now times 2 divided by 2.016. Okay, and then divided by 3. All right, this is what I got here. I got here 3.37, and it's going to be a little 3 here. Okay, so now this is what I got now based on 10.2 grams of hydrogen. All right, so which one is a limiting reactant? Of course, will be the one that produces smaller number of moles of the product. And so which one will that be? Of course, this is my winner here. The winner here is this, because based on 15.2 grams of nitrogen, you will produce now smaller number of moles. It's as if we remember how we guys handle the tops in here, produce the small number of tables. So this was the limiting reactant here. So this is now a limiting reactant, which I'm going to abbreviate LR, and this will be now the excess reactant. So in other words, when now the hydrogen will be reacted with nitrogen, this amount 15.2 will be completely consumed to make the product, this product here, where this one will still have some leftovers, will be unreacted. Some of this will be leftovers. Okay, now, so, but what's the mass now? What we're doing, guys, actually, we're calculating what's called a theoretical yield in here now. What is a theoretical yield? It is when you turn the reactants into 100% of the product. When this reaction goes to completion, this is what's called theoretical yield. So you got no more reactants left. In other words, the entire limiting reactants consumed here. And so when you turn these reactants into 100% of the product, you get the mass of what's called theoretical yield. And so theoretical yield, I'm going to put here mass will be in grams, and that will be now found by converting the moles of the limiting reactant here, based on limiting reactant. The moles of NH3 based on limiting reactant here at 15.2 grams into the mass. 1 mole of NH3 is 17.03 grams of NH3. And of course, this is just the molar mass of the NH3. And so let me get now the theoretical yield in here. It's 1.085 times 17.03. And so I got here 18.5 grams of NH3, guys, will be produced in this hypothetical, I guess, perfect reaction when you completely turn the reactants into the products at 100%, at 100%, pretty much 100% you turn the reactants to the products. Now, in the actual life, it doesn't happen this way. You most of the times get the product converted, I mean, 50%, 60, 70, 80%. I mean, occasionally get 100% conversion, but again, most of the times when you do the synthesis reaction, as this one here is a synthesis reaction, guys, remember from the previous discussion, or combination reaction. So you usually get a yield that is less than 100%. Let's say that, so now this is theoretical yield we found. Let's say you went to the lab and you did an experiment, you did the lab experiment. And what you found actually, what you did, which you synthesize here, instead of 18.5 grams, but 16.5 grams of NH3. This is what's called, guys, actual yield. Okay, so when you do the problems in this theoretical yield concept or percent yield calculation, it will be explicitly, guys, stated in the problem. You cannot solve the percent yield problem if you do not have the actual yield given to you in the problem. Okay, so how do you find out the percent yield? The percent yield, guys, is just found a simple matter. Theoretical yield here in the bottom, which will be now this 18.5 grams. On top will be actual yield. That will be your given mass that you got in the lab, or will be given in the problem to you, times 100%. Okay, so now all I have to do now is I have to substitute my numbers here. I made it a little too big here. Let me just erase this one here. Okay, so let me plug my numbers in now. So I got in the bottom the theoretical yield 18.5, the actual yield 16.5 times 100%. There you go. So now let me calculate the percent yield. And that will be now 16.5 divided by 18.5 and then times 100%. Since I got 3 significant figures, my final answer will be now 89.2%. And that's pretty much all I wanted to cover in chapter 10. So now I completed, guys, chapter 10. Let me just again reiterate that the limiting reactant problem is when you have reactants, 2 or more, and the amounts of these reactants are given, guys, in the problem. And this is the clue, guys, that you have to do the limiting reactant problem here. Take the mass of each element or a compound, whatever, guys, you're reacting here, and convert, guys, into the moles of the product. And then always compare which of the reactants, masses of which reactant will give you the smallest number of moles of the product. You're going to choose that as a limiting reactant. And then in the next step, you will find what's called a theoretical yield. This is the maximum amount of the product you can, guys, produce, guys, based on the amounts of each reactant given in the problem. Now, when you got a regular stoichiometrical problem, stoichiometry or multimole ratio problem, not a limiting reactant problem, you usually will be given just a mass of one reactant. Okay, not usually. It's pretty much you're going to be given just the mass of one reactant. And the other one going to be either not mentioned, that means you have to assume it's excess amount, or it will be mentioned that it's excess reagent. And then all you have to do is you have to handle it the way I handle, guys, a calculation of theoretical mass in the previous video. And so that will be just the mass, theoretical mass, yield found for the product based just on mass of one of the reactants that is given. But again, limiting reactant, very important, guys. You are given the masses of the 2 or more reactants, and that's where you have to find out which one will be limiting, and based on the limiting now amount of the limiting reactant, you will be figuring out the moles of the product. And so those are the moles, the smallest number of moles you will choose to calculate the theoretical yields now of your product. And so the percent yield, all you have to do is just use the formula. Percent yield is equal to the actual yield, which will be, guys, given to you in the problem, because you have to go to the lab and actually do the synthesis of this reaction. And the theoretical yield, of course, you just saw how I did the calculation for theoretical yield. There it is. This is my calculation, guys, of theoretical yields. And that's where the 18.5 went in the bottom here. And 16.5, guys, came from here. And I plugged it right here as actual yield times 100%. And so if I ran this reaction, the percent yield for this reaction would be just 89.2%. And that's, guys, the end of the presentation for chapter 9. So I'll see you guys in the next video when I'm covering, guys, the last chapter of the course.